Hi folks, and welcome back to Physics with Captain Rod. Let's see, I'm making this video here to provide an example of calculating the centroid of a three-dimensional geometry here. So what we're going to do is we're going to try to calculate the geometry of this salad bowl looking thing. And this curve, like in the yz plane, is defined by the function y squared equals 2z. And the first thing I'm going to do is talk about x bar and y bar. So the geometric center of this object is, I don't know, maybe something like this. And its x-coordinate and y-coordinate both have to be 0. So I'm just going to state right out front, x bar and y bar is 0 due to symmetry. And this is really going to boil down to calculating z bar. All right, so what you do is you break the problem up into little elements. And in this case, the elements we're going to want to use are little disks. I've already generated a couple of those here for us to chat about. So you got to imagine taking this 3D geometry and breaking it into a bunch of these little disks. This is just one of a whole of many such disks that run vertically. And you must realize that as we move higher and higher and higher in this geometry, the radius of that disk right here, this distance gets larger and larger and larger. And the radius is equal to, let's see the y-coordinate here along this curve. The centroid of the disk is here at its geometric center. Whoops, got that off a little bit. And right there is the z bar for the disk. And what we're going to do is we're going to take that value and we're going to give it weight by multiplying by the volume of this element over here. I drew another one over here to the right here. So we've got a radius here which is equal to, looks like y. It has a thickness. Now that's a differential, I'm going to call it a differential variable in the z direction, so we're going to call that dz. So the volume of this element, dv, is going to be pi times the radius squared times dz. Now, if I imagine this being infinitely small, then the volume would be infinitely small. If I were setting this up to do numerical work in Excel, I might call this delta V instead, because it would be a finite measurable value. But we're going to set this up to work it with an integral, so we're going to use a differential thickness, which leads to a differential volume. All right, so we take the z-coordinate times the volume, pi y squared dz, and then these get added up. Now, what I haven't gotten in the picture here yet is that this height is 2 feet in the picture I'm using. And this total radius right here is also 2 feet. All right, so we're integrating with respect to z. So we're going to start at 0 and integrate to 2. Now, so what we're doing is we're averaging z by giving it a weighted volume. And in the end, what we have to do is divide out the total volume. The volume of this is pi y squared dz, and again we're going to integrate that with respect to z from 0 to 2. All right, let's see what we get out of this. So let's see. Integral 0 to 2. Now this is already set up pretty nicely to integrate with respect to z, so that y squared looking right here is equal to 2z. So this is going to be 2 pi z times z is z squared dz over in the bottom. We're going to have integral 0 to 2 pi times y squared, and y squared is equal to 2z dz. And let's see, I'm going to need a little more room here. All right, top integral now, we're going to have, let's see, 2 pi, and then antiderivative z squared, z to the third over 3, and that's going to run 0 to 2 in the bottom. This is going to be 2 pi, and that's going to integrate to z squared over 2. Evaluated 0 to 2. These will factor reduce, so that's going to be 8/3 up top. And what is that? 4 over 2. 2 over 1 in the bottom. So it looks like 4/3. 4/3 feet. And taking a look at this, it's 0 to 2 from here. And if you look right in the middle at 1 foot, You see how there's more volume above the 1 foot than below, so it makes sense to me that our z-bar should be bigger than 1. Looks like it's slightly larger, so I'm pretty confident in our results. So again, this video is how to set up an integral to calculate a centroid of a 3-dimensional volume. I hope that this helps. Have a great day. I should say a 3-dimensional volume with cylindrical symmetry. All right, back to have a nice day.